Can you confirm if you're able to see the presentation screen?
Yes, sir. The screen is visible.
Thank you.
Thank you, sir.
I guess we can start at 9:35. People are starting to comment, so 2-3 minutes more, I guess.
Yes, sir. So we'll be starting in another 2 to 3 minutes. Around 75 participants have joined. So if you
Sure.
suggest, then we can start now as well.
Yeah, means let's start. I can start introducing stuff and giving background.
Yeah, okay, sir. So good morning, all the participants. Aditya, sir, all the coordinators joined today. So we welcome you all to the 9th day of the program. So with this, I would request Aditya, sir, to please start with the session.
Thank you, ma'am. Thank you for the coordination. Good morning, everyone. Today, with the FDP program, our target is to continue in the first session with the implementation flow using this course. Now, as you can see, we have covered a lot of this programming overview. We are targeting this section today, CTS and routing. And then we'll do the final sign-off section tomorrow. Now, the agenda for today is the clock tree synthesis part. With the clock tree synthesis, before we dive into the details, I want to give you an overall perspective of what all we have done to reach this stage. What we have done is we did the synthesis using USS. We then learned different stages of floor planning. We did different steps in the placement. What do they mean? How do we do macro placements? Now, finally, the question is, how do we make the clock reach the design? So before we discuss how do we do it in the tool, what are the steps? It is important to understand why do we do clock tree synthesis. So as people start to join in, let's see if just to start the discussion, I would like to ask this question from the participants here. Why do we do clock tree synthesis? if anyone who knows about clock tree synthesis can get, or if you have been following the designs up till now or the lectures up till now, why do you think there is a need to do clock tree synthesis? I'll wait for someone to write an answer. Okay, to minimize clock skew. Okay, so start with that point. Okay, good point. Okay, so let's draw a design here. Okay, this is our SOC. Okay, we have a block here, we have a block here, we have a block here, we have a block here. Now I have a IP which creates clock, say a PLL. If I assume the points mentioned by some of the participants to minimize clock skew, right? Suppose I take this clock and just short all these. Just connect the wire to all of them. Then as long as this wiring is symmetric, my clock skew would be almost zero, right? If this RC of these wires is and will be equal if they are symmetric. And if I send something from here, they'll roughly reach at the same time. Then what is the need for clock tree at that point? There is no tree here. I just created wires. Why do we need a tree? Well, it is an even distribution, right? There is nothing uneven about this. And you'll maintain synchronicity. First of all, what does the term tree mean? I want. Okay, Deepak is pointing out to distribute clock and minimize delay. Why would we want to minimize the delay? Why do we care that the delay from here to here is minimized? There is no requirement for the delay to be minimized. Okay, Surya Krishna is pointing out that there will be subnodes. Okay, I'll keep doing the same thing for the subnodes. I'll keep making wires which are symmetric. I'll keep distributing using the same method. As long as I do a symmetric interconnect distribution, why do I need? Okay, then the next point someone mentioned is if the length of wire is more, RC delay would increase. So what if the RC delay increases? I don't care as long as I send the clock from here and it reaches symmetrically to all of them. Why do I care? What the goal of the clock tree till what you have learned is to minimize the skew between the two flip-flops so that you do not have setup and hold violations and your ST assumptions are true, right? I'm sending the clock from here. I'm saying to every node, I'll create a symmetric wire distribution so that RC to every flip-flop is the same. But we are meeting the timing spec, right? Timing spec with respect to the clock is that you make the clock have minimum skew so that your other things are well synchronized. Why do we need to put any buffers in between? Is my question, I guess. So let's see. Okay. Okay, then there is a point of to improve the signal strength. Why do we want to use buffers to improve the signal strength? Why do we care? You only care about making the clock reach the if the presumption of creating a clock tree synthesis was to minimize skew, right? If you want to minimize skew, then you don't really care about maintaining the signal strength. And there is no real, as long as you can maintain equal delay, Surya Krishna, there is no point of reducing the delay. There is nothing you achieve from reducing the delay. Okay, I understand everyone. So what everyone is saying here is now I have a driver at the, let's make this. I have a driver here for clock. I need to send clock here. And if this wire is too big, then the slope of this would be bad, right? But why do you care if the slope is bad? As long as, didn't you guys till now study that if as long as the clock reaches symmetrically, then you can time this thing with respect to this thing. You have to minimize the skew. That's what you said, right? But wouldn't the rise time and the pulse width be the same? It's a symmetric wire to all of these. Sure, Divyansh, that's one of the use cases. Maybe you need to do there, but in general, if considering the situation I'm giving you, why do you need to put buffers? Why do I need to do this to make this sharper? Sure, insertion delay will be more, but as long as it's skews minimized between different blocks, why do you care about that insertion? Okay, there is a point of noise margin. So what noise margins do you want to maintain, Gopal? Yeah, means it loses its, again, so everyone is pointing out the same thing. It will start to look like this, but it reaches symmetrically to all the flip-flops. Why do you care? I want the answer to come from your side. This is the best way to learn about clock tree synthesis. I have noticed in many times teaching this concept. Otherwise, people do not realize why they are making this huge tree. Nope. It will not. Means as long as the clock is symmetric, it doesn't affect the whole setup anything, right? The delay, your delay is not dependent. Your setup and holds are not dependent on the delay. They are only dependent on the making sure that the clock reaches at the same or the relative clock skews. Well, again, Pradyuman, no. As long as your clock reaches symmetrically, you don't care. Means you have a valid point. Okay, that's a one valid point which has come up. Let's acknowledge that. Okay, good point by one of you guys now, and Harish is also pointing a good point. Okay, let's start. Okay, suppose we have a clock which looks like this. Okay, let's make a clock. What is this? Let's assume the time from here to here is 1 nanosecond. Okay, so the clock period is 2 nanoseconds. Now, suppose I pass it through a driver and there is a huge wire load in this. Right? There's a huge wire load. RC is crazy, like I'm talking about. Now, what will happen to the signal? this signal will start to look like this, something like this. Does everyone agree? It might reach full VDD swing, but it might do this. Eventually, a situation might come when this might not even reach VDD in every cycle. So you start losing clock cycles. Okay. So one of the challenges to create a good clock tree distribution is to be able to send the clock for the given frequency. So you decide how much buffering you want to do based on the frequency. Basically, if your frequency is high, then it is harder for you to maintain that edge. So your RC has to be lower or your buffer size has to be bigger to maintain the edge, to maintain the frequency. Otherwise, your signal will lose clock cycles. You are not able to send the clock correctly. Your clock will not look like a clock is the reason you put a buffer in between. So now if your RC is high, now let's think another way about this. Okay, let's see. Okay, so now ideally you wanted to send, suppose this. Okay, you wanted to send something like this. But what went out was something like this, suppose. Okay. What is good about this and what is bad about this? As long as we are able to maintain the frequency, why would we like to have this is good? Why is this thing over here good and why is the one at the bottom bad? When it reach, I mean, why are we saying we would write like sharper edges when the clock reaches the a flip-flop? Why do we care about this? Why do we not want this, but we want this? One reason I already told you now, that if you do not maintain enough buffering, then eventually it will start to look like there is no, means it will start to look something like this. You lose clock cycles. So as long as you don't lose clock cycles, why do you care that you have a high enough slew there? What is the need to for that? Anyone wants to take any guess? Well, this case will consume more power. If you maintain higher slope, it consumes more power. Okay. So Manikandan is pointing out that if we have this, then there might be some issues with the latches. Sure, we are using flip-flop for that. Satvik is pointing out noise margin. Okay. Noise margin, interesting. Can you explain more? Noise margin is definitely a region. Sure. What noise margin are we talking about here? There are a lot of different kinds of noise margins. It's a good answer. Well, setup and hold violations, how, Gopal? I am just saying clock reaches all the flip-flops, but it looks like this. As long as they make the decision here at VDD by 2, this is your threshold or threshold point is this, they make the decision here. Why do you care? Every one of them make the decision here. No. So why do you care that your slope is bad? Slope will come in the intermediate region of noise margin. Okay. Let's work with that assumption. Interesting point. So I am saying all the flip-flops transition here, right? Or if all the flip-flops transition over here, why do you care that what this slope comes in the middle of? Means you are, it is the threshold for all of the flip-flops is the same, where they will eventually lead to the same setup and hold time. Will the point where they make the decision is the same, right? Why do you care for this to be like this? Why do you want it to look like this? I think people have almost reached the complete understanding. Naveen is saying due to duty cycle jitter and latency. Yes, that is, the latency is not the correct point to be considered here first. Jitter is the more important point. Agreed. So let's start with that assumption. Jitter, and what will that do? So if my clock looks like this, why will we have jitter? If my clock is looking like this, why will we have jitter? You guys know everything. We have to just come up, discuss it, and figure it out, this problem. Everyone knows fundamentals of CMOS. We are just trying to answer. These are all questions which get answered from fundamentals of CMOS. There is agreed, Pradyuman. So because on the differences in the rise and fall time, if we do not maintain a good slope, the duty cycle will vary, and that will lead to jitter. I agreed. That is a very valid point. Completely agree there. So if you're not able to maintain the duty cycle, that eventually leads to jitter. Harish is pointing out that if the clock is more prone to noise at the transition, absolutely. So let's absolutely correct point. So let's understand, where does the noise injection in the clock come from? So if the clock looks like this or this, right, you cannot have any noise effect, because what can noise do? Then noise cannot shift it below zero, or it cannot make it go above VDD. Means even if it tries to do that, there is a big power rail sitting there which changes it back to the same value. So noise doesn't have effect in these regions, or has a very minimal effect. Noise has effect in these regions where you are not VDD or ground, where you're not, your power supply is not actively pulling you in one direction. Now, if you change this region to this region, if you make it bigger and bigger, the more effect of noise will exist. So to avoid this huge buildup of noise in your clock trees, and to be able to make the clock reach as a clock, so you have the correct frequency duty cycles delivered to your all your flip-flops, is one of the reasons why you create a whole clock tree buffer distribution. Okay. So your clocks looks like a clock, and you are actually able to maintain the frequency. That is why we create a buffers in between and not just short it with wires. Now, there is another reason. Let's think of this reason from some of the initial work which we did. So initially, if you guys remember, I said if your rise time is more or less, your what does that determine? Your gate delays. And similarly, if your rise time of clock is bad, your flip-flop performance in itself goes bad. It will go bad in all of the flip-flops. Your skew will be matched, but your performance, that clock to queue delay, will be bad. Your setup points and your hold points will be bad. So based on what slew you operate at, your flip-flop has different performances. And that is determined by the lib file, which Puneet explained you guys. So that's why design of a clock tree is always a trade-off between how much power do you want to spend on the buffers. If you put more buffers, you are putting in more power, and ideally you would like to reduce that, right? Now, but you still want to maintain enough slew rate that you do not add noise. Now, if the second point I made was the only point of concern, right? Let's take another example. Suppose I did this. This is my clock source over here. I want the clocks to reach here, 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 here. Assume that these distances are huge, in the order of millimeters, multiple millimeters, okay? Now, if I just wanted the clock to reach here, right? What I can do is I can just put a very tiny buffer here, and that would make this RC huge. And even if I send this, it will read something like this over here, right? Very bad. But if I put a tiny buffer here, and if my flip-flop is small here, then it will still look nice and clean, because this buffer will only see the flip-flop load. So my signal going into the block is still good, but what is coming to it is all over the place. So you have to, this is where the noise injection, jitter, and everything is getting added. You can still maintain a good slew rate going into your design, but you have to also make sure that this slew rate before that design is not bad, because that is where all your noise injections will come to. So then what you do is you'd say, I put a buffer here again. That will clean up the signal a little bit. And now the question is, how much do you want to clean up here? Just enough that your noise doesn't affect you, right? Because if you put a buffer just before your flip-flop, then you'll still have a nice transition. But in order for the jitter to not build up, you just care of barely enough powering it. So this is the whole trade-off space of clock tree synthesis, which comes up and which has to be understood before you actually go and do a clock tree synthesis. Because in complex SOCs, this is what comes up. How much, if in low power SOCs specifically, you want to put as less buffers in the clock tree as possible. Now, if you want to put as less buffers in the clock tree as possible, how do you do that? You have to trade off between the noise which will get injected to the buffer insertion. So you have to maintain the clock, but also not put too much power in the clock. And the higher frequency you scale it to, the harder it gets. Do people understand this? Anyone has any questions or points they would like to add on this? Less buffer means less area, less power, but it means you may not be able to transfer the clock, or you may not be able to transfer the clock cleanly with the noise constraints, basically. There's always a trade-off between area, power versus noise. Noise is then boils down to timing. Anyone wants to ask a question, add a point here, we'll proceed otherwise with the next few slides on clock tree synthesis, and then we'll go and look at the tool environment. Well, Pradyuman, the only way to reduce this skew is to minimize the wire, to match the wire delay, right? We already discussed. Skew can be minimized by wire delay. You are not adding buffers to match the skew. You are adding buffers to maintain the slew, SLEW, slew rate, rise time, fall time. During ASIC design, how clock tree buffering and all predicted and done before fabrication. Okay. So clock tree design is actually done a lot from experience, honestly. So you, by experience in a given technology, you have a decent knowledge of, okay, if my design is few millimeters, how many buffers are expected to be put in there for a given clock frequency, and it comes with, it takes time to get that experience developed. So that is why you have such powerful open source tools with you, right? Get that experience. Try to build different clock trees. Try to see if you were able to successfully do it for a given skew and slew. You can do all that. Absolutely. And I mean, so if you insert too many clock buffers, it also creates problems from congestion, crosstalk, and all that perspective as well. So there is a trade-off there. It's also, so there is no good way to predict what is the optimal point. Tools expect, so just letting the tool run blindly is one way of doing it, but it will not be an optimal answer. But tools expect you to be able to guide with what kind of design you want to do, basically. And this information, how many buffers, which buffers, what is based on the frequency, how do you design the wiring, how you place the blocks, that all has to come from the designer. And that knowledge develops over time. The more you practice, the more designs you run, that the more it develops that knowledge. There is no like a ultimate guide which is sitting somewhere where which you can just plug in. It is case by case, design by design, that you get that. Okay, nice. Then I would go through the one of the earlier slides I actually did. So just repeating what I said before, if you have a clock source, you can do an even distribution in order to maintain a different good enough slew rate to reduce the noise. We add buffers at with sizing as needed. Then the clock tree with the matched skew, as long as the distribution is matched, your skew would be matched, reaches some blocks. In the blocks, then you may continue with this symmetric distribution, or you may actually just short the blocks using different approaches of clock tree. There is a skew buildup possibly wherever there is not miss. So as long as you don't create an H-like symmetric distribution or some other symmetric distribution, you will have mismatches and the skew will build up, which you need to account for. Now, suppose now the next question in clock tree distributions is, suppose you have a block here and a block here. Suppose this block contains, let's call this 100,000 flip-flops. And this block again contains, say, 50K flip-flops. Up to these blocks, let's assume we did this wire length and this wire length assumed to be equal. So this is equal to 0 up to these blocks. Now, if there is a timing arc from this block to this block, would you still maintain a symmetric clock tree distribution up till all these 100K flip-flops? So will you keep doing this H tree up till all those flip-flops? Or will you do this as a clock? Now I'll just short multiple of them at some point of time using a single buffer. You'll lose the symmetry at some point of time. What is the trade-off between this to this? Here, what is the trade-off between continuing with the H tree to having a different approach of not maintaining the skew? Can someone tell or guess? If you keep doing this, what will happen? What will go wrong if you keep doing this symmetry? What is the cost we pay for maintaining the skew? Absolutely, power and area. So maintaining edge trees and skew costs us a lot of power. And if you actually work out numbers, it grows exponentially here. So you tend to at some point give up that exponential basically. Now, with this thought in mind, what we are going to do is we are going to actually boot up our tool environment again and try to run the clock tree synthesis and also actually routing first. And then we are going to give me one moment. Then we are going to come back and understand some routing concepts as well. Okay, I'm having some issues again with my SSH server, so I'll fix that in the moment. I would advise everyone to boot up the tool environment. And in the tool environment, you should actually, you should actually run the Pico RV32 up till the placement stage. Okay, boot up the tool environment, run everything up till the placement stage. So let's see. What do we want to do? We want to do /home. Okay. Having some network connectivity issues in my terminal. Let me fix that. In the meantime, just boot up the tool environment up till the basically the placement stage like we discussed yesterday for Pico RV32. Give me 2 minutes and I'll fix this. Okay, let's try again. So we want to go here and we want to do export of PDK root. Then we want to go in the open lane directory. We want to load our Docker. And then when we want to do the same thing as we have been doing. Give me one moment. Let's just see if people are asking something in the Q&A. And okay, queries about floor plan. We can come back to those, Naveen, in a bit. Okay, flow.tickle, design of Pico V32A. And then we want to do the tag, and we want to do test E&ICT. And we want to do the overwrite and then the interactive. And we'll run synthesis. Then we'll run the floor plan. And we'll run the placement. Now, before we go and run the clock tree synthesis, which is actually just one command in the open source tool environments, people are still improving the clock tree synthesis stages, possibilities in the open source environments. Still work in progress, but let's try to understand whatever we have, what can we do, and how can we actually in future make meaningful decisions with this, okay? So let's go here, then we'll go in open lane, and we'll go in the configuration directory. Then we have, let's do more on the CTS. So in the CTS, you'll see that there are few settings, clock tree synthesis, whether you're doing the clock tree synthesis or not. There is a target skew and tolerance. Basically, let's try to understand what this means. The target skew value is specified in picoseconds here. What is the skew you want to target? So if you create a clock tree, what is the skew you can live with is specified over here. And the tolerance is if you are not able to, for example, hit that value, how hard do you want the tool to try? So the bigger value you keep here, the lesser the tool will try to achieve that skew. So those are the only values which are available to you. You can change these and try different iterations. Towards the end, I'll give you a regression script also where you will actually try to run this regression using different clock frequencies. So the clock period we will change, and we will then try to hit different clock skews based on that clock period with different tolerance values. And we'll see in some of them, the clock tree synthesis will be very fast when will run. In some of them, it will not be able to run. So we'll come back to the regression after reviewing the routing scripts. But in general, these are the knobs you have, and you have to play around with these to make your designs work. Now, the question would be how do we do it in the, if you're not able to do it, how can we optimize in the open source environment? Then the answer is you have to create smaller block hierarchies, because in the smaller block hierarchy, you actually, if you have smaller blocks, you can do better clock tree synthesis in them, then do a better hierarchical design. Like we showed you last time, in last lecture, you do then macro instantiations of those smaller blocks and build a hierarchical design. That way you have better control and you are targeting clock skews, clock designs into dedicated blocks. You are guiding the tool on how do you design the clock on a very small level. So that is the only way to get done a better clock tree distribution if you have lesser knobs available to you. So now in terms of the tool environment, the only command to do is run CTS. And if you do a run CTS, it will actually try to see where the clock is, what the, if you have whatever clock name you define, it will look for it and build a clock tree distribution for that. So let it run that. Okay. And if you do run CTS, you should be able to get something which looks like this. And after the CTS, what the output which has given you, it has created a file in the synthesis directory, which has now clock tree information included in it. You can go and look at this Verilog file. This will have clock tree buffers in this file now. So I'll give you a few minutes to actually run this clock tree synthesis run CTS command at your end, let it finish. And then we'll actually move on to the routing stage of things. We'll run a few routing commands. Routing takes a while in the design, so then we'll actually go run the routing commands with, we'll understand the configurations for it. We'll run the routing command, and then we'll actually understand the routing theory a little bit because people have been requesting for that. So we'll first understand configuration of routing, run routing, and then go to understanding routing in the slides little bit, because routing will take a while and it will run in the background. So I'll give you 2 minutes to run this. So timing analysis happens after every stage. Vishnuvardhan, your tool will give you a report on different placements. So if I can actually just go here, I think over here I saw, let's just keep, or you can actually go in the log file of placement and it would have run. The timing analysis, so let's see here it is loading up your STS scripts. It is trying to do timing violation, and see here, over here, it actually did timing analysis and it analyzed that it was able to meet the timing basically. So that's the whole point of making an STA lectures in parallel, right? We have been having STA lectures in parallel. You can take any of these output. So for example, you can now take this Pico RV32A and take the SDC and actually run the timing analysis. And I think Puneet has some of that planned as well. He'll show the different Verilog files with a few constraints. How does it affect in the STA? It's a Verilog file. I mean, we can go look at it now. It's a regular Verilog file. So let's see. So whenever you have such curiosities, you should just actually go and open it. It said put it in the synthesis directory. So indeed, we have a CTS or CTS Verilog file. So let's see what it is, what's in it. So it's a regular Verilog file, but you'll see there are a lot of buffers which would have been inserted. There'll be a lot of clock buffers in here. It's a gate level netlist, regular Verilog file. Basically, you can go and analyze that. So after synthesis, what we have to run, Surya Krishna, we have to run the run floor plan, run placement, and then do run CTS. I think you are opening some other file. I mean, make sure you're opening this file, which is output over here. It should be a gate level netlist. Okay, so with this in mind, we would like to then proceed to some of the routing stages. So let's see what configuration variables do we have available for the routing. Okay. Designs. So if floor plan is giving error, Surya Krishna, you must have done some settings in your global or local configuration files from yesterday's work, which is causing it to fail. Okay, so let's do configuration. Let's look at what all we have in the routing. So in routing, there are a lot of these configuration settings which are available. I've explained some of them in the slides. We'll code them when we look at the slides. But I want to emphasize on some important aspects over here. We'll later on, because routing takes a while to run. It means if I leave it running, it will probably take like 15-20 minutes maybe. Depending on your PC speed, it might take half an hour as well. So we don't want to do multiple iterations here. It wastes the time of the sessions. You can actually change these variables on your own and run them, but I will explain some of the important ones. Okay, so this is obviously the minimum metal layer, maximum metal layer. If your design doesn't have that many layers, then obviously it will not be able to use it. It references to the PDK directory. There are different kinds of routers. There is a global router, there is a local router. There are options to set those global and local router settings. The first one is how many cores of your PC do you want for routing, because routing is a complex process. Yeah, it is processing heavy. Then there are certain unidirectional settings, whether a layer just runs in one direction. Do you allow congestion? How many times do you want to iterate if you are not able to meet the timing? I will go, I have written detailed explanations for all of these in the slides. I want to explain some of the basics of routing first before we take a deep dive here. Then we will actually come back to these and try to visualize them again. In the meantime, what I would advise you to do is I would advise you to actually just type run routing and leave it running in the background. Okay, so just type run routing and just leave it running in the background. It will probably take a while to run. Depending on what settings you have in your scripts, it might run quickly or it might run very fast. So just do run routing. I have typed it in the answer boxes. Okay. So this will take a while. Okay. So that means that you probably deleted the pin order config file or something. If check whether a file exists in the path, Rayesh. The error speaks for itself. Okay, we'll leave it running in the background. Now we want to approach some of the topics of routing. Okay, so what we want to visualize is we want to actually understand basic how does routing happen and what are different parameters available for you to play with it. But before we do that, I would request everyone to take like 2-3 minutes and actually just run the run routing command in the background and just keep it there. I can show you what's happening in mine. Basically, it's taking, like it's saying 10% complete with 0 violations. Slowly here violations will develop and then it will try to fix them. It takes a while. Sometimes it is able to, sometimes it's not. Depending on that, we change our utilization, placement density, and all that for us to be able to make it run. I'll also in the routing slides, I'll show you if it is not able to run routing in dedicated areas, then what do we do? What settings do you change with respect to the blockages? So we'll look at that as well. Okay. Let it run in the background, take a few minutes, let it just do this. We'll take 2-3 minutes and then we'll start with the slides part of it. Okay, so now we'll proceed with the slides part of things. As you can see, it's building up errors, violations, and this is the 0th optimization iteration. So it will go through all of it, then in the next iteration, try to fix them, and it will keep on doing. Now we need to understand what it is actually trying to doing. So let's look at that from slides a little bit, okay? Okay, so routing. What we need to understand is what is basically going on in routing and what is the concept of layers. I want to first revise that for us, and then what do we mean by blockages? We want to look at that concept a little bit. So just for a refresher, we had the standard cells. This is something which we already discussed. We have abstract views of those standard cells, which guide the router where all it has to do the connections, different ports, different what are the different tracks available to it, wherever can it route different levels of metals, it is able to figure out through the left files of basically your standard cells. Okay. Now, again, with respect to the design, your standard cells are connected like this, then flipped over. Then there are different vertical and horizontal routing metal layers available to you. Now, the question for the router is basically, are there enough tracks for you to be able to connect everything? That is the question you have to answer. Okay, so this is your routing over here, your routing over here. The question is this enough for you to route your whole SOC? Okay, that is what we have to answer basically. So let's take a step back and try to understand this little bit. Okay, let's take an example from here first. Okay, so with this, let's take this and let's take this. Okay, so if we have something like this, in this, suppose you are, okay, this is useless highlighter. Let's take this. Okay, suppose you want to do routing in horizontal and vertical. So let's assume your M2 is vertical. Sorry, let's make this horizontal, M3 as vertical, and so on. Okay, so you need to figure out how many M2 you can fit, right? So 1 M2, 2 M2, 3 M2, and so on. Now, these M2 will have some minimum distance to each other. Based on that, you know how many of these you can fit. And also, they will have obviously some width associated with them, right? That will look actually like this. So if you know your standard cell row track height, you are able to know how many M2 you are able to fit here. Similarly, based on your design width, you know how many M3 verticals you'll be able to fit like this. Because by standard cell library, you will know what is the pitch you can have them at, what is the minimum width you can have them at. So you have a general notion of the routing capability of your design basically. How many M2s you can fit in the horizontal direction, how many M3s you can fit in the vertical direction. And then if you continue with the same, if you have more metal layers, then how many M4s you can fit in the horizontal direction, how many M5s you can fit in the vertical direction. Based on the dimensions of your design and based on your standard cell height, the tool is able to figure that piece of information out. Anyone has any doubts on this or wants to ask a question there? Do you guys understand how, if you have this information and if you know the pitch and the width of your different metal layers, then you'll be able to figure out how many of those you can fit in an area. Any questions on that? Anyone has any questions or people understand what I'm talking about? Everyone knows what I'm talking about? Okay, good question, Surya. Only single metal layer. No, so in general, you consider all the routing resources available to you. So if you have M2 to say M5 available to you, so you will consider all the routing tracks of M2 and M4 in the horizontal direction and all the routing tracks of M3 and M5 in the vertical direction. Did that answer your question, Surya? I'm just coming to macros, Gopal. Give me just a moment. Any other questions by anyone? Okay, this is from the standard cell perspective. Most of if your design is consisting of standard cells, so that's from the standard cell perspective. Now let's try to understand it from the SOC perspective as well, with respect to the maybe multiple macro instantiations. Okay. Yes, good question by Uma Bhargavi. Wherever you have metal distribution, you cannot assume it for routing basically. Otherwise, it will short with PG absolutely. So when you do top decisions of which layer is involved in what, basically you make an early decision. So if your as top level metals are only for PG, which level goes for PG, which level is available for local routing, and which level is available for global routing. So you try to figure that out early basically. So Pradyuman is asking, is it possible to connect M7 with M1 only? With M1 only, but without any. Okay. Let's try to actually answer that using something like this. Okay. So let's assume we are trying to connect M5 to M1, right? So if you have to connect M5 to M1, it has to pass through all this. You cannot delete all this and just jump here. It has to pass through all these intermediates. There is no way for you to skip what comes in the middle. Did that answer your question, Pradyuman? I'm coming to your question, Harish. Give me one moment. It will be explained in next few explanations I give, that question and the macro question. Okay. Okay, then continuing on the discussion of how how something like an SOC routing happens. Suppose you have, let's take this. Suppose you have a big SOC, right? Let's make this like this. Now, let's assume you have a macro sitting over here and a macro sitting over here, maybe. And the rest of it, this is all standard cells. Okay, this is all standard cells. Now, in particular, closer to your macros, there is all, because these macros have a lot of pins, there are a lot of routing constraints. You have to route a lot of signals here in a very small area. So the exact analysis I said for the standard cell routing layers, the tool does for the macros as well. It tries to figure out, okay, I have to route, say 100 signals to this macro. Do I have 100 channels available for me to route here? If not, then it sees congestion. Similarly, on the vertical direction, it says there are 200 pins I have to route to this. And do I have 200 tracks, vertical tracks available to me or not? Otherwise, it sees congestion. Right. So that is how it tries to figure out whether it can route to a macro or not. Now that first it has figured out what is the routing tracks available to it, what the tool does is it divides your design into bigger chunks. The tool will divide your design into bigger chunks, basically like this. And then it will try to do, okay, what is the amount of routing resource available to me here? What is the amount of routing I actually have to do here? Can I do all that? this again here, it will try to do all that because it with the row and vertical and horizontal track estimation, it has know what is the requirement, what does it have, can NI do this, right? It does a global routing approximation. It right now it only does an approximation. Can this be done? Once it does that approximation, then what happens is the tool is then able to figure out, okay, now that I've done that approximation, do I have all the available resources or do I not have all the available resources? If it doesn't have available resources, then it will error out at that point. If it has the available resources, what it will do is then it will start creating those tracks. Till now, no tracks have been created. It is just doing approximation. Then it will start creating those wires. Okay, then it will start putting those connections in place, right? It will do vertical, horizontal connections to wherever they have to go. And then through between different regions as well. During these connections, then it will, so this is called the basically track assignments. Now it is assigning tracks to different routes. Now it will, okay, this will, in the first stage, it only actually approximated, does it have the resources? In the next stage, it assigns different available resource to different actual wires, actual nets. In the last stage, which is the detailed routing stage, what it does is it then is able to actually create those wires. Actual physical mass of those wires are created. When the actual physical mass of those wires are created, what happens is there are situations where, suppose this wire extends like this, then the minimum page DRCs are not met. Then it has to do further optimization of fixing these issues. So routing is a multi-step process. First, you do a global approximation of the resources, then you bin your design into different parts, again do a routing approximation, resource calculation, then you do track assignments to figure out which resource will be allocated to which net. Then you draw those nets. And then at the end, you actually fix any issues which come up when you draw them. So in stage by stage, you are able to perform different routing tasks. That's why routing takes a lot of time. It's a more complex process than the usual one. So as you can see, it is now in the trying to do the second optimization iteration. If it already ran for you, then it means that you had some settings which were which made it easier for you to run. I might have made it really stringent settings somewhere in my configuration file. That's why it's having a hard time running it. So this is the basic routing flow. Any questions on this? Anyone on this routing discussion we just had? So Harish, in open source tools, no, it is not able to do. In the commercial tools, there are different application options available that you can make some small tweaks in placement. Naveen, those are just routers which are available in different tools. There are different routers, different actual routing algorithms run in them. Sure, Prathaman, you can that you try to do it in the placement stage itself. Actually, you try to approximate what happens where, and you rotate them for the best pin orientation to reduce routing congestion. All the macros. Well, that was your task role. Means we gave that as a task. It will take a lot of time to actually do that, but we gave you the whole macro placement thing. The only thing you have to do is instantiate it in there, right? In the open source tools, visualizing congestion, I'll show you. It actually puts it in the script. In the log files, you can see that it actually tells you the routing layer congestion available to you. It is not able to do it with respect to spins and cells. It does give you a routing layer congestion report. I can show you it in the log file in just a bit. We'll go to again config file in a bit. Naveen, yes, I'll actually have a little bit explanation here. I want to go in what those different configuration file settings do. Vishnuvardhan, what do you mean by route abutted blocks? I'm not sure. Yeah, I mean, again, abutted blocks is something I don't understand. What do you mean routing for abutted is, I'm not able to understand that question. I'm sorry. Okay, in the meantime, I'll come back to the question which was asked. Okay, so there are different knobs which are available to you in the configuration file environment. Again, I don't want to change them because it might take a while for you to fix them and change any knob, and your routing will take like forever as it is taking at here. So routing is a time intensive process basically, as you can see. And also with respect to the question that was asked by, I think, Harish or some, I don't know, but it actually tells you the routing capacity and overflow in both horizontal and vertical directions in the log files. You can look at that. Okay, so with respect to routing, you can set the minimum layer, the maximum layer you want to use for routing. Obviously, if you have a PG ring, it will not route there. It will, suppose if you have don't have the layer in your technology, it cannot route there. Then there are some adjustments you can play around with. Basically, you can reduce the routing capacity between different cells. So you remember when I said global routing, it created different bigger hierarchies. If it split the design into bigger chunks. So what is the routing capacity assumption between the chunks? You can play around with some adjustment ratio here. Then how big of that global cell size do you use? That global tile, or how big of it do you use for global routing approximation? You can set that as well. Then you have how many optimization iterations you can do during your routing. So once it is trying to actually do the final detailed routing, it will make a lot of errors. How many iterations do you want to do there? That will be needs to be basically, you can set that. Which global router do you want to use? There are different global routers in this OpenLAN environment which work. Some of them work better in some case, some of them work better in some case. You can change that. And also which detailed router do you want to use? You can change that. After all this, I actually want to explain you some concept regarding the basically obstruction, and we'll come to that. In the meantime, let me actually take questions. So Surya Krishna, right, you still same. Please go back to the previous lectures. We cannot cover everything back from synthesis again right now, so that is not a feasible point. Okay, so let's going from the bottom, tolerance variable in our config files. Oh, okay, yes, so basically the tolerance variable, what it means is you've set a target skew, right? So how hard will the tool try to meet that target skew? there might be cases where it is not able to meet it. If you set a big tolerance, then it will try very less to meet that. If you set a very small tolerance value, then it will try very hard. It depends on how much time you want the tool to spend on the clock tree synthesis. I want to aim to give you guys a regression script at the end of today's session as well, where you can set a regression and try that. Okay, then the question, Naveen, if I change the core dimension, it affects VLSI. Definitely, your core dimension affects your size, affects your delay, your amount of buffering you have to do, definitely. So ESD, crosstalk, IR drop, yes, they're all related to routing, but not within the scope of this couple of our sessions and implementation flow sessions. Naveen, we cannot cover that within the scope of this program. The question about changing orientation of IPs, suppose an IP has orientation left and right. Sure, you can obviously rotate your IPs. There is no question in that. There is no issues in rotating your IPs. Okay, how do we do routing over? Again, what do you mean by no gaps between blocks? That you cannot have blocks which overlap their pins. There is no way to create such blocks. You can have a block where a pin of one is just connected to the pin of the other, and then that would mean that by abutment there you have already done your routing. Okay. Number of metal strips in vertical direction has any dependence over number or bit length? Increase number of metal strips. I don't understand your question. I mean, I'm sorry. Number of metal strips in vertical direction has any dependence over number of bit length? The number of metal strips in the vertical direction is just how much resource is available to you for routing. So Harish, I'm coming to your question. I'll now try to explain a method of creating an obstruction for routing. I think I need to check whether there is one for placement. Yeah, we can look. You can go and also look in the OpenLane literature. I think there is not in the OpenLane. There is no placement obstruction or blockage, but we can definitely check later. Okay. Any other questions? Okay, now let's see what happened to the design I ran. You can also go, maybe yours finished, but my still is stuck with these many violations after even the third optimization. So clearly it will take some time in my design. I might have set harder configuration variables. Well, you can actually, good question. You can actually do this. You can, let's see. In the configuration folder, there is a README. Whenever something says README, you should go and read it. And it tells you everything for all configuration variables for different stages. See? Did that answer your question, Roel? Perfect. Okay, so I want to target two things because this routing is going to take a while in the background. I want to actually explain the concept of blockages in the meantime, and the routing finishes, we can try to apply it or If it doesn't, we can you can go and try it, apply it on your own after this session. The goal for obstruction is something. Let me actually go and explain it from some diagram over here. Suppose there is a, when you actually do a design, there is an area in your design after, so you can always look at post placement depth, right? You can always look at post placement depth, and you observe that there is a region of the design which might cause congestion with respect to routing. So what you can do is you can tell the tool to create an obstruction there to have lesser routing to that region. So you can mark regions in your design where you want to have lesser routing density. These might be regions right next to your macros, for example. So right on the boundaries of your macros, because you want to restrict those layers near your macros for the connection pins of the macros, you want to mark those to have lesser routing in them. So you can mark regions in your design to have lesser routing density. That should be one of the goals. Now, you can do that by setting basically this in your config file, in your config file for your design, not in the global config file, in the config file for your design. Which one is this? Let me just show you here. So not in this folder. Okay, I think it got disconnected. This one also got disconnected, so my routing run would have been killed. What I'll do is I'll restart in the I'll restart the run with some other settings. But in the meantime, let's continue with the explanation, and let me open a terminal. Okay, where did it go? Okay, here. Okay, so which configuration file do we need to do this? We need to put it in your design configuration file. Any environment variable you want to set specific to your design goes in your configuration file. So this, if you want to set a routing blockage, what you do is you go here and add it in this configuration file over here, and then that region of the design will have a routing blockage in it. Okay, now the question is, what do these different X and Y coordinates mean? So which layer do you want to block? Maybe there are macro pins in that layer, in that area, you want to block them. And your X and Y coordinate of your bottom left of your rectangle routing blockage and top right. And similarly on, that would mean that on metal 5, you can mark it from 00 to 100, 100. And in the next figure, as you can see, from 00 to 100, 100, it would have marked a routing blockage basically. Any questions on why and when do we want to apply a routing blockage by anyone? Yes, so you, in this tool environment, you definitely have to rerun it. Absolutely. So, yeah, okay. That's with respect to the routing. Well, Harish, in the in the open source, it's very hard to do these relative things. Some of these you can, some of them it's very hard. So providing absolute numbers is easy, but doing all this relative to the macro, that it moves with the macro, all these are, you need to explore. Some of these are possible, some of these are not. It just is just, not all options are available in open source, basically. Okay, so now similarly, can actually go and make it somewhere else and so on. So we can do this. No, rule, it will not give you an error if you just leave it and forget. Nope, it doesn't matter. It will not give you an error. Okay, so before we actually complete the I actually want to explain regression flow to you guys as well, and that's something which I initially thought I'll not cover in this course, but I added that because I think it's quite important for everyone to understand how you can make use of the power of this open source environment, how you can, because it's not license bound, right? You can run any number of iterations of this. So it helps you analyze whatever is possible. So I added that specifically, and I want to go and show that to you guys. So I want to let you know some of the sign off commands and what to do there. Some of With respect to explanation of these different stages, there will be sessions by Puneet in the next day, which give you detailed explanation for these. But I just want you to know what are the commands in the OpenLane environment to run that. So you can run it on your own and then you can match it with Puneet's explanation. Okay. So first of all, you have to run event to do LVS layout versus schematic. He'll explain you what exactly that does. You have to write a Verilog with power pins in it. So first two commands actually does that for you. You write a powered Verilog file with these first two sets of command. Then magic is your tool to actually run the different DRC LVS scripts and also export your design, your spice netlist for the design. So first you run magic, then you run an spice export, then you run DRC, then you run LVS. So this is with respect to DRC LVS. This is to first two are to create your LVS netlist. And then the last one is to run an antenna check whether you have any antenna issues in your design else or not. Again, as I mentioned, some of these DRC issues, what they are, antenna issues, what does DRC mean, what does LVS mean, all that will be covered by Puneet in a subsequent lecture. But I just wanted to give you the commands from the OpenLane environment. You can run these commands in your, after you have run the routing, these are the leftover commands. These take like 5 minutes to run most of these things. So I just wanted to leave this at the end on the implementation flow side that you should complete it with this. You can match it with Puneet's explanation on DRC, LVS, and extraction. Okay, that's the general plan. So Manikandan, yes. So Puneet will come into detailed explanation of what these different stages are. With respect to the OpenLane environment, how do you run those detailed stages? That I just wanted to have a command list available to you. these commands, Naveen, are same as as you said, run routing, then you say write powered Verilog, means these are space as you just wrote in your OpenLane environment. It's the same thing in the Docker. After you've done the flow tickle, you run floor plan, you run synthesis, you run synthesis, floor plan, placement, CTS routing, and then you do these. No change in the file or anything. You just run these commands right after the routing. It's the netlist one also there itself. Okay. Yes. The powered Verilog one is in order to LVS, you need a Verilog file which has the VDD and VSS information captured, which is typically not done in the standard cell libraries. In the implementation flow site, you have to specifically write the ones with the VDD and VSS captured. Okay. So, any more questions? Okay. Then the last thing I wanted to do is I want everyone to be able to understand the concept of regression. Okay. So what do we mean by regression? When do we do this? Why do we need to do this? And all those things. So if your routing is done, that's fine. If not, I would advise you to open another terminal. Just load your OpenLane environment, your Docker in it, and we would like to load your export PDK, and we would like to actually set some files for you, and then you can actually just run them in the background. So just open a Docker. What we'll do is we will actually not use Pico RV32 because it will actually take more time to run this test. We can use a smaller design to quickly show you the power of regression, and then you can actually do this later on. Okay. So what we can do is okay. So we'll go here. We will go to OpenLane. We'll go in. So that's what Manikan, depending on how you wrote the RTL, your clocking speed may vary. Then that's why we want to try to figure it out. What is the maximum your design can support? That's the whole point we're trying to understand with the regression. So let's go to a design, smaller design called SPM maybe. In this SPM, I want us to be able to create a file called regression.config. Okay. So let's try to create a file. Let's call with the clock period. Okay. So let's make it vim regression.config, right? Vim regression.config, right? Which looks like this. Okay. So I want to create a file vim regression.config. And in that file, I'll put a regression on just the clock period first. And let's do a regression on this from 1, 2, 5, and 10. Okay. I just want to, for now, do a regression on just this. So we created a file called regression.config in my design directory. So which design did I pick? I picked the SPM design because it is a small design. So in that design, I went inside its directory and I created a file called regression.config. In that file, what I did, I have just written clock period is equal to 1, 2, 5, and 10. I'll do this and then I'll let you do this. Let me try to go first explain the whole concept. Okay, then I'll give you like 10-15 minutes and then you can try to do this on your own. So first thing is you create a regression file. The contents of the regression file will look something like this. We're only trying to set the regression on the clock period first to determine what is the maximum clock frequency we can run this at. Okay. Then the next thing is we run the Docker. So let's go and run the Docker somewhere. Okay, let's do this. Okay, cd sport pdk root. Then we do the Docker running. And then in this Docker, what we want to do is we want to run this command. Okay, we want to run this command. I will copy paste this command for you. Okay, in your directory. And then before we do this, I want to leave the above slide present for you so that you can actually create a regression.config at your end, and then we'll try to run this. Okay, that's how we'll try to target this. So I'll leave this file up for you and I'll paste this command in the chat box for now. So try to create this file, okay? And I'm pasting the next command in the chat box. If it's routing, you can just open another terminal, Kanti. This is a different design. We are doing just a test in a small SPM design. So it just open a new terminal and run everything in parallel. It should be fine. Yep. Try to create this config file and then run that command in your Docker. repeat. You have to save the file in your SPM design directory. That's where you have the regression.config goes in your SPM, because we'll test it on a small design called SPM. Okay. So that's what you do in the Docker. Make sure you pass the paths correctly, otherwise this will not run. What we can do is, since people are just completing this, we can actually take any doubts on this tomorrow in the tomorrow's session. We can take doubts on this quickly if people were not able to run this. I'll put this in the slides up in the repository. You guys can try this regression, and after that you can actually ask doubts tomorrow, basically, since we are short on time with respect to the first session. And I wanted to actually introduce this concept to you because this is a very powerful concept, and especially for researchers, this can be very powerful and they can use this. Yes, Naveen, just this command. Not in the open lane, you have to run this in your bash Docker. After loading Docker, basically. Okay, there must be then, okay, I think I'll let, the way we can proceed is I have these slides. You can actually refer to these slides. And I think in the last command, I might have missed this double dash in, you have to try these double dash as I put in this slide. And that should fix your issue most probably, George. If not, you can actually I'll put these slides up. You can actually try to run these after today's session and we can take doubts tomorrow, okay? So, and with respect to some material on what you can do with the regression, okay, I can actually have a small discussion on the next session on what is the power of regression and what we can do on that. How do we set different settings on that? Sure, we can do that. Okay, excellent. So as I mentioned, I'll leave these slides with you. You can give this a try. This is a very powerful tool, and hence I added this to the course for everyone. What I want to actually ask now is, we discussed a lot of content today, starting from clock tree synthesis to routing to regressions. Does anyone have any generic questions, which people missed? Then let's target that. The errors with respect to regression, I'll put the slide deck up. You can try this on your own and try to figure these errors out. If not, we'll try to address some of this again in tomorrow's first half of my tomorrow's session. So, keen on frequency analysis, explore. So basically, frequency analysis and limitations are actually done from custom. So a lot of clock tree estimations are first using custom simulations in SPICE, and then doing noise estimations in SPICE, and then how those reflect in actual clock trees. It's the clock tree synthesis and design and clock frequency analysis is itself another whole research area, basically. Well, after routing, I have a list of commands. You can actually just run through those commands. They'll be in the slide deck, which will be posted today. So you can just run them. If I come back to them, these are the commands which you have to run. Okay, any other questions? The concepts behind these commands will be actually explained to you guys by Puneet in today or tomorrow's session. Okay, so that's how we'll proceed then. What we'll do is we will look at quickly into what is the power with the Docker, and then we will actually quickly solve your doubts about the regression. We'll take a look at the power of regression, and then there is some low power implementation flow concepts which I would like to let you guys know what are the main aspects of that which you should know about. We'll try to cover that in tomorrow's session with respect to this implementation flow course. Okay, so that's how we'll proceed. Harish, I'll upload the slide with the commands. You can follow that. You just have to load the Docker basically. So this slide should be better explanation for you. So where you get this bash, you load the Docker, you get this bash basically. You have to reach there and then run this command. Okay. Routing is time intensive, George. It takes a long time, depending on what settings you have it at. So that's part of. So that's with respect to this error. Please follow my slide. This slide should give you an idea of what command to run, where to run. So I'll post the slide and then you can try to fix this command of regression. Any other questions? The error in regression is fine. We'll try to post the slide, then you can do it after this session, and then tomorrow we'll address it again if needed. Gopal, we tried to split it between my talk and Gaurav sir's talk, and Puneet captured some other aspects of my work. So we split it already in our talks. based on what Gauravs are captured and what's left, and we'll capture the leftover material tomorrow, and then we'll work that way. Yes, so don't worry about this. I'll let you know with this slide. Okay, nice. So then we are all on the same page. That's how we'll proceed. We'll cover some leftover low power concepts tomorrow, and we will look at some issues with regression as needed tomorrow. And yeah, then the leftover concepts of sign off will be covered by Puneet. Excellent. So yes, then Firoza ma'am, over to you. I think we are done with respect to today's agenda. I'll send you the slides in 5-10 minutes, and you can upload for participants' usage.
Thank you, Aditya sir. Thank you for your wonderful presentation in day 9 of this FDP. So we request all the participants to have a break of 5 minutes. So after 5 minutes, we will start with the next session. Our next session will be taken by Mr. Puneet Mittal sir. And also there is one announcement from our end. Today the MCQ2 will be conducted from 1:15 onwards. The link of the MCQ number 2 will be open for 30 minutes. That is 1:15 to 1:45. So all the participants are requested to visit the link. The link is already provided in the drive. So from there you need to click on the link and solve the paper. Please make sure that the auto submit button is not there. So you need to solve the paper and submit it. You need to click on the submit button to record your answers at our end. Thank you.
Ma'am, can you just give me sharing rights?
Yeah, we have provided you the sharing rights, sir. Please.
Okay, let me just check it.
Okay.
Is it visible?
Yes, it is absolutely visible, sir, at our end.
Okay, great.
So we will start by 11:31.
Okay, thank you, ma'am.
Thank you, sir.
Okay, so I think all of you are back. Okay, so let me see. Let me just tell you what is the agenda for today. So first of all is good, like you guys are very active. I can see that particular thing. And I'm happy like the way, so the way this workshop is going on right now, I would say is awesome. At least I'm happy to see the way you guys are responding, you guys are participating. I don't know about you guys. Like, okay, what's your take for this workshop? But things are good, and I'm sure like you guys are also learning a lot. At least it will help you in an n number of ways. Okay, so just use a Q&A window and just say yes or no. If you are back, just say yes, we are back. Or maybe you can just write yes. I just want to know, like, okay, all of you guys are able to hear me properly or not. And can you guys see my screen? And I also want to see how many of you are going to respond to my today's session within my session. Okay, audible, visible, no, so slides are visible, am I right? Not me, or maybe I have to check camera, yeah. So my camera is off. Okay, great. Yes, slides are visible. Okay, so yesterday we have discussed and I tried to cover almost everything, whatever I can do in such a short time about STA. Now, today agenda as per the agenda sheet, it is something related to the LVS DRC parasitic exception. And Aditya also gave you a little bit idea about few commands. So what I will suggest you run those commands once and just see uh, how those commands are going to behave. But what we are going to do, just one second. So what we are going to do today, we are going to do the two things. Like yesterday, we missed couple of a lab interaction, I would say, the hands-on, so open STA portion. So I'm just going to show you a couple of commands in a very fancy manner because I don't know how many of you got a chance to run these commands. So that's something I will just give you an idea. Like, okay, these are the things if you're going to change this particular part, how other things are going to be different. And from the analysis point of view also. So whatever we have discussed till now, we have discussed a lot of conceptual side, different command side, those things we have discussed. But if in a report, if you have to do the analysis, and in that particular analysis, if you have to understand, then how you're going to understand that particular part. So I will just spend some time in discussing that particular thing. And the second portion, or you can say after this I'm just trying to cover within a half an hour or so. And after that, I'm going to discuss about parasitic extraction, few things about DRC rules. What are those DRC rules? And yeah, I think that's this agenda for today. And like a few of you were asking, I saw about the low power thing. So you don't worry. That's something tomorrow we will cover a couple of things. Not me. Maybe it's not required. Like okay, everything I'm going to cover. It's between me and Aditya. So Aditya maybe cover a couple of things, and then the few things about the sign off, I will cover that particular part. So like Aditya mentioned, we restructured couple of things and we shared couple of things as per the availability, as per the time we have. So that's agenda for today and tomorrow. Okay, so Naveen was asking it is still pending to generate netlist SDC and Sdf file that is used during floor plan. Oh, okay. So see, Naveen, that's what I'm just saying. I'm going to just show you a couple of things today, and then you guys can try yourself. Like, okay, these are the things we can do. You guys can do that particular part. So like from the very first day, I am I'm just making my point very clear. See, there are almost how many people are here? I think there are around 300 candidates are here, and everyone have a very different skill set. Few are very good, few are on a basic level. So uh, as as a you can say the instructor or as a trainer or maybe as a industry people, what we are expecting, like okay, few of the things you guys should do yourself, and but yes, we guys should be like your should give you the direction. So that's the purpose of today thing. Like practically I will just show you a couple of things, and then we can see like okay, what best we can do. So Aditya is spending a lot of time on the tool just to give an idea about the open lane. And if you will see my approach is a little bit on a different side. I'm just giving you the uh, tool, not the whole tool chain. I'm just focusing myself on a single tool. And there also, I'm just giving you the concept related thing and how you guys can do yourself the tool part. So that's the something uh, I'm just making sure like okay, you guys can do things yourself. And in the same fashion, Aditya is also just helping you with the commands. He's showing you each and everything from RTL2GDS with the different netlist with the uh, different design. So if you remember the very first day, I gave an idea to everyone that is going to be a session where you guys, if you guys have your own netlist, you can do everything end to end. That's the same thing we are doing, and we are also just trying to make sure like okay, you guys can go in the deeper in the script and just change the script also, not just the design but also change the script. Okay, so let's come back and here uh, let me okay, so let me just show you one more directory, so which is like by default uh, if you're going to do things yourself uh, using this OpenSCA directory, so you will get this particular directory there. So in this directory, if you will see, they have a couple of SDF files, SPF files, stickle files. So I want to just show you the syntax of a couple of SDF files. So here, which one? Let's see this SDF file. So it will give you an idea like, okay, how these examples are going to help you. So very first day, I told you like okay they have some default examples and you can just try those default examples also. So now if you will see the SDF syntax here, So let me just go at the top, and so this is my SDF file. And this SDF, some basic setup is there, and then the cell information is there. So this is a cell. So this is a cell type, which type of cell it is. So they are talking about the top. So in our design, which we are using as a serve top, so there is going to be the serve top, and in that particular serve top, it will be like some interconnect values will be there. So right now here they have interconnect values with respect to their example, the example which they were using. But from this syntax point of view, if you will see, SDF is going to be something like that, and how it is going to be useful and how you're going to read it, how the tool is going to read it, I will just show you from that particular angle. So here, if you will see, so they have some input pin, and there is another pin. So consider this, these are the two ends of the wire. So IN1 and R1D, these are the two ends of the wire. And then these are basically two set of values. Now two set of values, since we are talking about the rise and the fall, so one set of values are with respect to the rise, another set of values is with respect to the fall. So it is in that particular fashion. Now within this rise, you will see there are three values, 1, 2, and the 3, and they are separated with this particular column. So these three values are basically with respect to their three corners. So like worst corner, typical corner, or the best corner. Or you can also say it is like minimum value, maximum value, and some typical value. So you can go in that particular way. So for the rise also, you have now three corner through three corner value. So this SDF file is going to help you to understand, like, okay, if you have a typical library, if you have a uh, best case library, worst case library, then which delay tool is going to pick from this particular SDF file. Now here they were talking about the interconnect, so that means interconnect delay, this is something we can find out from here. Okay, now someone was asking, like, okay, these programs are written or generated. So now this program, in the sense, this particular file, am I right, Surya? So if you're talking about these files, yes, these files are generated by the tool. So SDF file, so this is a SDF file. So SDF file is written by the tool. So how the tool is going to write the SDF? So first of all, you have to understand what is the SDF file. So SDF file is a delay format file. Okay, now this is the delay format, SDF. Now, how the delay is written, you can just check the delay, and then I will tell you from where these values are coming, how the tool is going to understand these values. So now this particular value, so here you can see this is the interconnect. Now we were talking about certain cell type DFF1X1. So this is some flip-flop, and that particular flip-flop, now they are talking about the delay. So now you remember in a dot lib uh, we have certain delay for the flip-flop, and that is a clock to Q delay. So here we are talking about the clock to Q delay. Now here we are not talking about the matrix. So if you will see in SDF, there is nothing like a matrix. Tool is not going to do any calculation in terms of a transition time, in terms of a delay. So here the values are fixed: falling, rising, minimum, sorry, worst, best, and the typicals. So that means that now these values are the fixed values. Even if you are going to change your input transition time, or if you are going to change the output load, these values are not going to change. So the if tool has to pick a delay value, tool is going to pick these constant delay value. So whatever the return, that is the delay value tool is going to pick. Now in that, again, if you will see here, they are talking about the setup. So positive clock, passage clock, that means the setup time at D, pause edge, and there are the three values. Again, the three values are basically in terms of best, worst, and the typical. Similarly, hold, and similarly, we are talking about the uh, time period also. So like, okay, these are the time period. And now for each and every flip-flop, these values are there. So the point is, in SDF, everything is fixed, everything is decided, everything is fixed. You cannot change any value as per the transition time, like we were discussing yesterday. So nothing, neither you can change it. Second, what just happened? Okay. So now let's see. I think screen is visible to everyone. Am I right? Yes. Great. So now let's see in our design when okay, so maybe I can just give in a little bit idea here what is inside this. Yeah, so I'm not showing any PPT. I'm just showing the terminal, and I was just explaining on the terminal itself. So now if you will see some example one.tcl file, if you want to just check it here. So here, this is the same flow, .lib, .v, then we were talking about wire load model. So we haven't discussed the wire load model till now. So I would say, forget about this particular part. Link design, read SDF. So read SDF syntax is this. And then these are the two are part of our SDC file. So SDC file commands, it is written here in this particular fashion, but you can also save these two commands in a .sdc file, and you can just source it here as a source, that particular SDC file, and then they are doing the report check. Now, if you will see here, I have just read this particular SDF file. So now let's see how things are going to change here. Uh, I just want to show you that particular part. So let's see. So now in this directory, now source, let me just directly source you because I just want to show you the difference. So if you're going to source it, you're getting something. So this is for some example.1 tickle with respect to that they have this particular value. Now on a similar side, let's do it. So here you just remember this particular table R2, R3, these numbers are there. Let me see if they can. So if let me just show. So what I'm trying to do now, I'm just trying to just show you only these things. Then what is going to be happen if I'm not going to read SDF file? I just want to see if okay, is going to be there any change which I can just show you, because if I'm not going to read SDF file, then okay, so design is already linked. Then okay, maybe I have to just do it. Okay. Okay, then okay, no issue. Okay, no issue. No issue. And then, okay. So now this is something 9.43. And what was the previous one when we didn't have, when we had a SDF file? So now if you will see in this particular scenario, so only the difference was in this particular scenario, in this particular case, I just source a SDF file. And in the, so here the slack was 6.20. Just remember this 6.20. And this is between R2 and R3, some 6.20 values there. Now what is here? Here the value is different. And here it is again, it is between R2 and R3, but if you will see, it is a 9.43. And what is the difference? So in the both the case, the difference was SDF file. In the first case, SDF was present. In the second case, SDF was not present. That's the only difference we had in these two scenarios. So I just want to show you like, okay, what is the impact of a SDF in your analysis? So basically SDF is the delay values, and you know, like, okay, this delay values are going to be this is something, these delay values tool is going to calculate from somewhere. Now, in our case, when the SDF was present, and when the SDF was present in SDF has delay values with respect to the net also, it has a delay values with respect to the cell also. So what the tool is going to do, since the SDF we have loaded, so tool is going to give the preference to the SDF. And if it will give the preference to the SDF, it will give you the result with respect to that particular SDF. It is going to calculate the delay, or you can say it will pick the delay from the SDF file. Now, in the absence of a SDF file, the tool is going to do the calculation. It is going to check the .lib file, and it is going to give you the exact correct value of a delay. So now there are two things. One is the accuracy. So if I will ask you like, okay, you have to give me a accurate result, then you have to calculate the delay every time. Every time you have to calculate the delay. And if the tool is going to calculate the delay every time using a .lib file or any other similar type of file, for the cell delay, if tool is going to calculate the delay from the .lib file, and for the net delay, if the tool is going to calculate using a Sdf file. So obviously, when you are going to do the calculation, you in the sense that if the tool is going to do the calculation on the basis of the input transition and output load every time, then it is going to take a lot of time. Now, in your case, because the design is very small, it is very easy for the tool just to give the result within a fraction of second, because it's a very few design, very few parts is there. So someone asked me yesterday, if the design is going to be the complex, then what is going to be happen? If the design is complex, the number of parts are more, and the more parts, then you will get the result in a in a more time. So practically in the industry, the results, this report check, the first time when you're going to run the report check, when the tool is going to do the calculation, it sometime take days. Like, okay, after one day, you will get the result of report check. Or in an industry, they are using the command report timing. So after one is because the tool is going to calculate the delay of each and every path, each and every cell, each and every net, and then it is going to give you some number. But every time you cannot run just like that, like number of just to run the report check, and you have to spend this much of time. Then what exactly you're going to do? You will say like, okay, let me see if I can do something, if I can read something, if I can write something in whatever the tool has calculated. So in the tool, in a timing analysis tool, see, even in the open source, you can see there is a file, and there are two commands. One is a read SDF, another is a write SDF. So someone asked like, okay, what is the source of this particular file? The source of this particular file is this particular tool. So this particular tool, the OpenSTA, what is the source of OpenSTA if you want to do the report check or calculate delay, if you want to do that particular part. So for the cell delay, we were talking about the .v, then we had discussed about the .lib file. And after that, you did the report checks, and after that, you tool calculate all the delay values for all the flip-flops, and it is calculating on the basis of the .lib file. After that, if you want to write SDF, you can write the SDF also. You can just write the SDF. So what I'm going to do now in our design, so the design which we were using, which was RISC-V design, and here we have discussed our yesterday we have this not yesterday, day before yesterday, we have sourced couple of files, and we have discussed like, okay, what is going to be my timing reports, and I'm sure most of you remember the timing report also. So let me just open one file here, so that you will come to know like, okay, no, SDF file is not the part of this thing. So I just took this particular file here. I took this report liberty, Verilog file, link design, only create clock, and some report check main, and I just also uh, took this particular max report, redirected, and I just write it in a particular file. So this is something the same which I have shown to you just step by step. I just created a file here. So what I'm going to do here, I'm going to source this particular file, and then let's see what exactly you will get. So source, and this equal file, and see, it is taking some time, and after that, now you have this result. So this is with respect to the minimum. Maximum we have somehow stored in this particular file. So if you want to see, you can see in this particular file also. But that's not the thing we wanted to do here. We wanted to write SDF file. So just for your information, so that you should not tell me like, okay, sir, you have some SDF file here. See, right now I don't have any SDF file in this particular directory, and this is the same directory. So both the directories are same. Let's see if I can write any SDF file. I'm just doing the first time. That's what I'm saying. Write SDF. I'm not going to mention anything. So if you will see in the help command, help write SDF. So there was a lot of options are there. But these are the things which you want to decide. If you want to write, you can do in that particular way. But I just want to use the default one, SDF, and then I have to just give a file name. So let me see, RISC-V.SDF. Okay. Okay, something is done. Now here there is a RISC-V.SDF file. Let's see if anything is present inside this file. Yes, a lot of things is present. So first of all, let's talk about the same section, the same thing. So this portion is there, which I showed you in a example.sdf file also. So that thing is there. It is what is the design name, what is the date when it is generated, and then what is the nano, that is a time unit. Then the cell, serve top, instance, delay. Now this is something with respect to the net delay. Now you know very well, like in our design, there is nothing like a there is nothing like as a net delay, because we uploaded, we gave the tool only two files. One is .lib and another is a .v. We haven't provided any file which can have the net delay related information. That means the RNC related information. So RNC related information that comes after the parasitic extraction. So since there is no such file, so a net delay is supposed to be 0 only. Since there was nothing as a some wire load model, so all the net delay is supposed to be 0 only. So that's the reason here, if you will see all here, if you will see, everything is 0 for interconnects. And see the complete design, complete interconnects, everything is here. And this is literally a big file. So if we want to check, let us check the CLK. Okay, maybe if I will do setup, yeah. So now it is a setup and hold. So now let's see the flip-flops and all, whatever we have discussed. So these are all the flip-flops or the cells. These are the cells. Like if you remember, after the net delay, there is a cell. So these are the cell. In that particular cell, there is a IO path, there is a pin. These are the A, X, N, and X. Now we are talking about certain delay for the fall and the rise. And we were just talking about the two worst and the best. So if you will see, those worst and the best, all those information that is written here. Now if you will just go below, then it is like A to Y. You can understand this is Y and A. So basically for this particular cell, output and input relationship. So in a similar fashion, like there is basically in a AND gate, input to output timing arc is there. For that particular timing arc, for the rising waveform, for the falling waveform, what is going to be the delay. So as per, after the calculation, whatever we the tool did the calculation on the basis of your current existing uh, design, what the tool already calculated all these values on the basis of the existing transition time and everything. Now after that, the tool figure out like, okay, this is your falling, rising, these are the values. And see here, you can see A to Y, the values are different, B to Y values are different. And if you will go with the setup and hold, then also you can see for this. See, they have mentioned very clearly clock to Q delay, post edge D, and the negative edge D. So for the negative edge, at D, if there is a positive edge, then what is going to be your hold values? If at D there is a positive edge, so that means at the D there can be two type of signal. One is positive, one can be negative. And if it is a positive, then these are the hold values. If it is negative, then these are the hold values. Similarly for the setup also, these are the setup values, these are the setup values for positive and negative. But all the flip-flops are going to be the positive trigger flip-flops. That's the reason they are saying like, okay, this particular flip-flop is going to be triggered at positive CLK. And then whatever the flip-flop, and all the flip-flops, you will see the similar kind of structure. The now next time, whenever you're going to read this particular file, next time whenever you're going to read this particular file, tool is going to pick everything from here. So delay values and everything, it is going to read from here. So that's the importance of the SDF file. That's the way you can write the SDF file. Is it clear? Any question till now? I think now you guys can understand like, okay, how you can write a SDF file. What is the importance of the SDF file? And SDF file is a single file which have all the information, everything. Guys, any questions? Naveen, if you have a question, just ask. Okay. You want me to wait? Okay. Okay. Now this is a very good question. So someone asked like, okay, if SDF is given, then .lib is not needed. Now, it's a very good question and it's a valid question. I was thinking just to answer, just to tell you this particular part when I have mentioned this thing like, okay, if you have a SDF, then tool is going to do the calculation using the SDF. Now, Harish, let's try to understand the importance of .lib. What you have done in the flow. So in the .lib, there are the cells, there are the cell names, and each and every cell has their own certain parameters in terms of power, in terms of a delay, in terms of the transition, even the capacitance, even in terms of uh, basic area. So those things are available in the .lib file. So basically, when you have a .v file, and in that particular .v file, if you want to make sure like, okay, uh, it is compatible with your standard cell libraries in your library. So there were three steps: read liberty, then read Verilog, and then there was a third step which is a link design. So if you don't have a .lib file, you will not be able to link your design. So .lib, we are using a .lib file for the multi-purpose. So it is basically, if you are not able to link your design, tool is not able to do the analysis, because tool will never come to know like, okay, what is the cell name, what is the pin name. Tool will never ever come to know that particular part. So that means .lib is required for the linking purpose. But inside the .lib, where we are talking about the matrices, the timing information, the timing arc, if now we are saying like, okay, if I'm going to change those values, so what is happening? The tool is doing the calculation every time. Now, tool is not going to do the calculation every time, because now we are talking about the SDF file. So even now, if you are reading a SDF file, if the tool is going to read a SDF file, if you will make any change in your design, which can affect the delay, like if you will make the change in the transition time. Yesterday we were talking about the transition time. Somehow, let us suppose if you will make change in the transition time of a particular waveform of a particular signal. So you may be expecting like, okay, what the tool is going to do? Tool is going to check the transition time. On the basis of that, it is going to calculate the delay, because that transition, because on the basis of that, tool is going to read a .lib file. In that particular .lib file, there is a matrix. The new delay should be there. But if you are reading a SDF file, so like I said, tool is going to give the priority on the SDF. And when the tool is going to give the priority in SDF, SDF don't have any matrix value. That means even though you have changed the transition time, tool is not going to give you the updated delay value. It is going to give you the delay value which is present in the SDF file. I hope I've answered your question. So the reason we are using a SDF file, because we want to fast. We want to just make our processing fast. Now someone asked like how to get the interconnect delay values. Yes, there are two other files which I haven't discussed, which I haven't sourced you. So there is a one SPEF file and there is a wire load file. So in the SPEF file there is a RC values and wire load file that has basically the approximate value. In RC file, in a SPEF file, basically what happened is like it will have R and C of a net, and then the tool going to calculate the delay value of the net. So if you remember in one of the slide, I have just mentioned the Elmore delay model. Uh, that particular day, I just said like, okay, you can read those slides. So tool consider those Elmore delay model and calculate the R delay value of a wire. Yes, so SDF just masked the value from the .lib file. Yes, Naveen was asking in an industrial tool what we performed, we do synthesis. We will read only following .lib, .v, SDC, we generate netlist. Okay, so netlist is the same .v, SDF, new SDC file. We never read SDF file during synthesis, but used SDF and SDC file at the synthesis level to post layout. Why we are reading SDF at a synthesis level? So answer, I mean, I think you're making question very complex. The question is now, let me just simplify this particular question. So Naveen is asking why there is a need of SDF at a synthesis level. Why we should read SDF at the synthesis level, and from where this SDF will come. Maybe that may be one of the question. So basically, like I said, SDF. What is a SDF file? SDF file has a delay, delay information, and that delay which you can read directly, which tool can read directly. Now that I'm not saying these delay values are the accurate delay values. What I'm saying, these delay values are calculated on the basis of certain calculation which tool did at a certain point of a time. Now if you are going for a design which is from the scratch, you don't have any idea about the design, what is going to be the delay value, then what is going to be happen in a synthesis? The first time when you're going to do the synthesis, it is going to consider everything as a zero. Then you will move to the next stage, and then you will do maybe the floor plan placement, and then you will come to like, okay, there are some delay values are there, but that's not the correct value, because with that those values you're not able to close the design. So what happened? There are certain things which is like an approximate thing. So we can use those values, those numbers back to the synthesis. Like, okay, initially I considered everything as a zero. Now it is like a delay value is at 10. Now you're going to reuse those values, and then you are going to run the synthesis so that the synthesis tool optimize the netlist on the basis of that delay numbers which you have provided. So I think all of you know this Newton Raphson method in your engineering days. So what is that? Like, okay, you don't know the solution, but you just put some value in on those variables and figure out like, okay, what is going to be your answer, and then you just see whether it is how much it is deviating, and then accordingly you just converge on the final number. So it's the same way, like you are playing with the SDF file. So that's the one purpose we are using the SDF file in the synthesis level. Second thing is there are a couple of macros. If you are using a particular macro, now you know everything is fixed. Someone else is already gave you that particular macro, so nothing is going to be changed inside that particular macro. But uh, uh, you want to use that particular in the sense, the macro in the sense it's not going to change, but that's something generated by you. So you know internal structure of that particular macro. So you are using that particular netlist as it is, and you know like, okay, you're not going to change this particular portion of your design. So what you're going to do, you're going to use the SDF of that particular block as, and you just give it to the tool, so that tool is just using, you're not going to spend time to calculate the delay value of that particular block. I hope, Naveen, I answered your question. So that's I think Harish, I think I already answered, like, okay, you can create whenever the timing tool or any tool did the timing calculation. After that, you can calculate, you can generate this particular SDF file, and the way it is going to be used. So you can use it in any fashion. So like I have just mentioned, like, okay, it depends on you how you want to use it. Now, one more thing on the same line I want to show you. So there is something known as derate. Let me just show you, because I think that will help you a lot. So there is something like set timing derate. So let me just do that particular part. So I'm just setting a set timing derate, and then minus, let us suppose is early. And for example, that number is 0.9. Okay, and enter. Now let's do it. Report checks. So now, okay, let me just do it in the report checks minus path delay min, because I did it for okay, so some number came. Now let's see if now if I will write a SDF, something will change or not. Write SDF, and this time I'm going to write it as a RISC-V2.SDF. Okay, now let's check it if there is any difference. So there are two SDF file, RISC-V and this. So I'm just using a diff directly here, just to show you, like, okay, is there any difference or not? So RISC and then, so there is no difference. Okay, so delay values. So let me just check it. That means they haven't consider the set timing derate value. So this is the way you can see, like, okay, what are the values, whether you were able to do that particular part properly or not. Let me just check it one thing, whether this is applied properly or not. If I will say 1, just give me 1 second. Okay, and after that, if I will say report checks minus path delay, it was there, but I think maybe okay, so it's supposed to be it's supposed to change. It's supposed to change here. Maybe it is calculating the new value after SDF. Okay, let me just check it. Maybe the tool is sometime there are certain restrictions on our open source. Let me just check it, or maybe I'm maybe I'm doing something wrong. Yeah. So let me check this particular part. Maybe I will just check it like why there is no change in SDF. But if I'm going to make any change here, it should make changes in the SDF also. So let me figure out. Maybe I will just come back to you later on. So one concept which I want to highlight here, that is this derate related thing, and in an advanced node, in an advanced, sometime we do this derating thing. So derating thing is just like in a multiplying factor. So in a multiplying factor, so you can see here, like I have mentioned, so 0.44 for the minimums because I gave a um, report check basically only for the minimum side. So like here we were doing it. So now you can see if I will just write it. So it is 0.44, it becomes 0.40. So that means it's reduces. So it's basically it is reducing in that particular way. Like okay, if you're going to derate, it is going to change uh, your delay numbers. Okay, so that's basically the timing derating related thing. What else I can help you right now? Uh, report checks. So I think that day I gave an idea about all these things, except there is a one thing which I just want to show you, this field related things. So if I will say report checks minus fields, and then if you want to write, I think you can write uh, all the values. Let me just try it. Oh, sorry. So now if you will see a cap, so I need a the report should mention this. So if you will just write in this particular way, slew is there, capacitance is there. Come on, so there is a command where you can just come up with the slew and the cap both at the same time. Let me see where is that command here. So field is there if you can figure out any other command. Just check it. So this, so okay, I will just check it. So right now, the thing which I just want to show you yesterday when we were talking about the slew. So if you want to do it, you can just check it in this particular way. So for every input and output combination, you can see like, okay, they are also providing you this slew the transition. Now, in our cases, luckily, all these flags are meeting, so there is no problem. But if in your case, if you are going to use, let us suppose any particular file, any particular design, and if there are certain issues, so how you're going to figure out like, okay, what is that particular issue? So in that particular case, see right now here you can see in the slew, if I will see this particular slew, so I can see like, okay, here it is 0.19. That means this is a high, this is a large value. So if the value is large, then delay is going to be on a larger side. So that's supposed to be one of the point which you can figure out like, okay, this is basically a large skew. Now, if you want to see the respective, like, okay, if this is the case, then what is going to be happen in case of a cap? So if you will just go here and if you will see in the cap range, so which cell we are talking about? We were talking about A2I, AI4. So here A2I, A5, AI4 is this. So in this particular case, if you will see, the cap is very small. So this is basically, we are talking about the output cap. So here what is happening, your output cap is very small and your input transition, if you will see, and that input transition on a higher side. So this, before this, yeah, so here we were talking about this particular slew. So in this particular fashion, you can figure out like, okay, where exactly is our problem? The problem is in a skew side, problem is in a cap side. Now, if I will ask you like, okay, what is in this? Where exactly the cap basically the load I'm talking about, where exactly the cap is high? No, so nowhere the cap is high. Everywhere the cap is either it's a 0 or it's a 0.01. That's all. And again, these are the values which is still two digit. Significant digits are 2. Now, if you want to increase the significant digit, then again there is a, if you will see the help command, in a help command there is a command, and there is an option like in a digit, this digit, and then you can write the digit also. So that means if you want to change the significant digit, you can change that particular part also. So in this particular fashion, we can check the report checks and we can just try that particular part. So for you, that's going to be a homework, I would say. So I gave you last time also, today also I'm just saying, you just try all these commands and then you will come to know like, okay, what are those commands which you can use for the reporting purpose. Okay, so Surya, you was asking what is a OR4, O22A, O21, etc. indicate what it is. Basically the nomenclature. It's a nomenclature. It's basically the name of the cell. This is the complete name of the cell. Now, what type of cell it is? So I think from the functionality point of view, I will recommend you just to go to the .lib file and just check it. So uh, I can write in place of this any name. I can also write Surya. If the and respectively I can. So this name is coming from where? This name is coming from your .lib file. So you can just go and just check the .lib file. I think that's going to be the best for you. Okay. So now I am going to finish this STA portion here in the interest of the time, and I request all of you to do some practice, at least on an individual tool. So as a part of a flow, you can you can do the analysis, but as an individual tool, at least you should know what to do, how to do, what are those commands, and in any point of a time, if you have to use the individual tool, let us suppose if you are not able to run standalone STA, in an open lane flow because of any issue. Maybe it is around the wrapper, the scripts are written in such a way, maybe you are not able to invoke that particular part, but you want to do standalone analysis. So in that case, you know how to, what are the files you should port from what are the files you should give as a input to the OpenSTA. Just you have to find out those files in your directory. So the directory which I have shared with you last time, so in that particular directory, all these files are present, like serve synthesis, top synthesis V, there's the CTS file, and similarly the optimize.v, so pre-route.v. As such, everything is same from the .v point of view. Nothing has changed, at least in my case. But still, I will. There are few changes, but yes, when it comes to the wire and all, those things has changed. But from the cell point of view, not much difference is there. That in your case, when you're going to use any particular design, so all these files after every stage you can dump out it .v file, netlist file. You can use that .v file in OpenSTA along with the .lib, along with SDC, SDF, SPEF file. You have to just source it, those particular file, and you have to do the certain analysis to understand like, okay, where is the problem? What is the problem? Where is the setup problem? Where is the whole problem? Okay. Okay, so Surya is asking very basic question, how to execute the file in OpenSTA. So what is your I'm confused, like, okay, execute the file in OpenSTA in the sense. So there are two ways. Like if it is a tickle, just source the tickle file. Or they have the commands, just like read liberty, read verilog, read SDC, read SDF, similarly read as SPEF. All those commands are there. So you have to read those commands within the tool using use those read those files using those commands within the tool. Okay, is it clear? Anyone have any other question? No question? Nothing? No question. Great, guys. Then let's try to start this slide portion related to some parasitic related things and some DRC related part. So this is the exception files. This is the exception data. That means in terms of the parasitic extraction, what are the different files you need? So first you have to understand the parasitic extraction. That means parasitic is, we are talking about R and C. So we are talking about that particular part. Now for to understand the to calculate the RNC, so RNC of a net. Now if we are talking about RNC of a net, so like Aditya also mentioned last time, it is all about the metal. So if you remember, he shared one stack diagram where the different metals are there. He also mentioned like, okay, there are metal 6, metal 7, metal 8, and in our design, in our technology, we are using metal 5. So all those things. So that means if in my design, if I'm routing, so the routing which we are doing, so that routing is, let us suppose, on a metal 1. And now you want to calculate the resistance for metal 1. Then that means in one way, other way, I'm talking about the metal 1 right now, and the metal 1, that means the technology related information. So if you remember the second, third day when when we had a discussion about input files, input output files, during that particular time, we have we have discussed this particular thing. Like, okay, in a technology file, there are uh, all the layers are present, their minimum weight, their weight related information, technology related informations are present. So if you want to calculate the resistance and the capacitance, then you have to make sure like, okay, you have a technology file. The second thing is you are calculating the resistance and capacitance of a wire, and you cannot calculate the resistance capacitance of a wire unless you don't know the physical information, physical location of that particular wire. What is the length? What is the coordinate? What is the height of that particular wire? Whether that wire is very nearer to the another wire or not. Because if it is very nearer to the other wire, then the capacitance value will be there. If the another wire is far from that particular wire, the capacitance is going to be very less. So that means you need a physical information. So in a parasitic tool, definitely you need a technology file and you need a physical information. And then we will talk about like, okay, during the after the parasitic section, you will get a parasitic netlist. So, or you can say you can get a parasitic data which will have a R and C with respect to a particular net. Now, just to give you an idea, so this is our metal wire and just a basic metal information. So in a 3D, we have W, we have L, we have basically the T. So those things are there. Just 1 second, guys. So this is a metal wire. So these two metal wires, now as a designer, you can increase the space between the metal wire, you can increase the width of the metal wire, and if you want to increase the length, you can increase the length of the metal wire also. So that's the reason I was talking about, like, now you should have a physical information about the wire. Now in this, that is the physical part. The technology part is from the thickness of this particular metal wire, because that's not in your control. So like you can see here, I haven't mentioned like, okay, you can increase the thickness of the metal wire because that's not in your control. That's the control in the technology. So that from where that data will come, that data will come from the technology file. What is the dielectric between the two metal wires or two layers? Because that's a something you cannot decide. That's a something the technology is going to decide. And on the basis of that, the capacitance is going to be calculated. So that means that information you can capture from the technology file. Another thing is from the fabrication point of view. So when the fabrication usually happen, so at ideally, if you are thinking like, okay, there are two metal, this is a space, this is the width of those metal wire. But after fabrication, we will get some structure like this. Now, we how this structure came? Then again, there is a whole physics and those who are from college, they are doing the research, they know very well. So this structure is basically coming because of certain manufacturing defect in the process. And even though Foundry tried to minimize it, Foundry cannot just escape and just make it as a ideal structure. There are a number of reasons. Just for that, maybe you can read the diffraction, you can read the diffraction of a light, you can read that particular part, you can read the etching, you can read the lithography, and uh, these are the things which you can read it, or maybe you can just go through, understand the complete fabrication process. And in that particular fabrication process, uh, you will come to know like there are several places where there are chances of uh, these type of manufacturing defects. So the point is, the reason I have highlighted this particular slide here, ideally, this is basically you want to achieve. Practically, this will come, but and because of this practical challenge, the industry, or you can say the foundry, they came up and they said like, okay, we should have certain rules so that there should not be any problem. What problem I'm talking about? Let us suppose if you have your wire less than minimum width or the less than the minimum spacing, then there are chances after fabrication they become like this. That means either the wire is going to be open, or wire can be short, two wire can be short. So to avoid these things, Foundry came up with a certain rules like minimum width, minimum spacing, and these things are present in our technology file. And in the technology file, there are there are matrices where Foundry will tell you like, okay, there are the width variation, there are the space variation. On the basis of that, the resistance can vary. So all those information is present in our technology file. And the parasitic extraction tool always consider those rules. Now, how they are going to consider, let's see. So there are two factors. I'm just taking an example of a width and the parasitic. So the width and the parasitic, all of us know very well, R equals to rho L by A. And when A come into the picture, it is basically the width into thickness. We are talking about the resistance of a wire. And on the other side, I have also mentioned width can be controlled, width can be changed. Designer has a control on the width. That means you can increase the width and you can decrease the resistance, because that resistance is inversely proportional to width. That means you can increase the width and decrease the resistance. But the second portion is capacitance. In the parasitic, the second thing is capacitance. Capacitance is epsilon A by D. Now, what is that A? A is basically the width and length. So if you are going to reduce, if you are thinking like, okay, I will reduce the capacitance, I will reduce the, I will increase the width, it is going to reduce the resistance. But if you will increase the width, it is going to increase the capacitance. So that phenomena, those things always consider when we are talking about the width versus parasitic elements. So these are basically the intentional change which as a designer you're going to do, and you're going to control this particular part. But during the fabrication, whatever the changes going to be happen during the fabrication, that's something is known as the unintentional change, which I have just discussed in the previous slide. Like, okay, that is a unintentional change. That's a something. First of all, it is not in your control, the foundry control. The second problem with second thing is, you don't want those changes. You want to minimize that particular changes, but still there are things which there are changes. There are variations, and that's the reason I'm saying unintentional changes. Now let's try to understand how these changes going to affect your parasitic thing. So this is your these are the three wires. These are the intentional changes. You just change the width of the wire, keeping space as a constant. So that's basically the intentional one. Unintentional is you have created these three wires, and then after fabrication, they become like this. Now you can see here in this particular case, the width increases, but the space decrease between those two wires. So space decreases and the width increases. Now, if I will say this S is minimum S, then here you can see it is less than minimum S, but you cannot control it because this is during the fabrication. In this particular case, if it is S, here also you will make sure either it should be S or greater than S. So that's a intentional change, that's an unintentional change. Now how it is going to affect, let's see from the capacitance point of view. So if we are talking about the intentional change, so width is increasing. So if the width is increasing, that means width is increasing. So if your width is increasing, we are talking about the two cap. One is the ground cap and another is the coupling cap. So ground cap is going to increase epsilon A by D. That means with respect to the upper and the lower metal wire. Resistance going to decrease the way I have discussed, rho L by A equals to W into T. So that is decreases, and from the coupling cap point of view, nothing is going to be changed because the coupling cap is not as a coupling cap don't have any dependency over the width in this particular scenario. So basically coupling cap is not going to change. Now let's try to understand in case of an unintentional change what is going to be happening. And in an unintentional change, you're going to, here in this particular example, width is increasing. Width increasing, obviously ground cap increase, resistance decreases. That's all of you guys understand this particular part. But in this unintentional changes, the space is going to decrease because the space between the two wires that decreases. And that's something it's not in your control. But the moment the space is going to decrease, the coupling cap is going to increase because the coupling cap is basically what? Coupling cap is epsilon A by D. Now this is A and this is a D. So you just decrease this particular D. So here this is basically epsilon A by S. Now S, if you're going to decrease, then the coupling cap is going to increase. So if I will talk about the total cap, so in this particular case, total cap is increasing. Now, by this, I think you can understand like, okay, why uh, we usually talk about the coupling cap. And remember, this coupling cap is indirectly related, not the indirectly, directly related with the signal integrity. That you will also come to know in a technology scaling side. So in a technology scaling, in the sense you are decreasing the width, you are decreasing the minimum spacing also. So if you will just decrease it, you will get something like this. Now here, if you will see the coupling cap, so first of all, width decreases, ground cap decreases, resistance increases. Okay. Now space decreases, coupling cap increases, and if the coupling cap is increases, that become critical, and then it is going to create a signal integrity problem. So SI, signal integrity, crosstalk issues, that's because of this particular part. Okay, I think I should check with you guys if you have any question. Okay, so any question? So Surya, good question. In a full custom design also, we are not having any control over it. So you are right. We are talking about the thickness. So from thickness point of view, that is a technology specific. If it is a technology specific, yes, You cannot technology directly. You don't have any control on these parameters. Okay, so there's one more question. Sir, how to correct a hold or setup violation using OpenSTA? See the corrected change in the open flow. So, okay, so got it. So think in this way. So the question is good. So question is like in a open lane flow, you have a netlist, and you came to know like okay, there are certain setup and hold violation. First of all, you wanted to fix it, and let us suppose you fix it with the help of inserting a buffer, and now you want to see those changes in a back to the open lane flow. So answer is very simple. Like when you're going to fix it, you're going to fix it in a netlist. So if I'm going to insert a buffer, you're going to insert a buffer in a netlist somewhere. And that netlist is a whether it is a physical or it's electrical, everywhere that buffer is going to be inserted. That means now your netlist has changed. Now if you're going to use the new netlist, then everything is good. Okay. Any other question? What is the impact of inductance of interconnect? So Aparna, inductance is also there. It's not like inductance is not there. It is like in a digital side, inductance, we ignore the inductance because if you're talking about then digital, it is a DC. But yes, in analog, inductance is very, very, very important. Okay. Any other question, guys? Hmm? No questions? Okay. That case, let me move. Let me just go on the next. Okay, so this is the stack which I already Aditya showed you. Like, okay, the foundry usually provided the technology file in this particular fashion. I'm not going to discuss too much about this here. Just for your information, like, okay, there are as a from the different matter layer point of view, different minimum weight, minimum weight, minimum spacing, thickness, all these things are different. Okay, and you can see the numbers which is provided by the foundry. So these are the numbers which is going to be provided by the foundry, and you can see how the numbers are changing from metal 1, metal X, metal Y, metal R, metal U, metal Z. So these numbers are changing in this particular fashion. So you should have just an idea like, okay, how things are there. Okay, so from the parasitic point of view, there are two type of parasitics. One is a device parasitics and another is a cell level parasitics. So these are the words which we are using in the industry. So device level parasitics in the sense when we are talking about the MOSFET, when we are talking about the parasitic of a MOS. So that's a device level parasitic where we usually talk about the CGD, gate to drain, gate to source. these type of parasitics. So just to give an idea, like, okay, if you are talking about the parasitics extraction, so parasitic extraction can also extract the device level parasitic also. So last time the metal 1, metal 2, metal 3, which I have just discussed between the metal 1 and metal 2, that is the basically the metal layer point of view, the cell level extraction we usually talk about when the cell is already there, and at that particular time if you want to extract, that means you're talking about the metal 1, metal 2, metal 3, these type of extraction, the parasitic race, especially the resistance and capacitance. In a device level, these are basically the different type of capacitance, and the tool can calculate this particular part. So in the lower technology node, if you will see how different capacitance are there. So you can see there are capacitance with the PCs, which is a gate. Now here you can see if there is a capacitance between the substrate, there is a capacitance between the basically actual source or the drain region, I would say the diffusion region, then the metal one also, then these there are the um, uh, this particular VR, which is known as the contact. So there is a capacitance between the poly layer to this particular contact layer. Now those who are doing some, I would say, research, or the research scholars, they can do a lot of work here, and they can figure out like, okay, how they can reduce these type of capacitance, and these capacitance play a very important role. So in the parasitic extraction, this is a complete different field in a MOS designing, and that's the reason when we are talking about the library, there are the different type of cells, different type of NAND gate, AND gate. So in a AND gate, there are different type of other configuration, like which type of PMOS, which type of NMOS you have used. So like in this particular example, there is a capacitance between PC and this uh, cut via, I would say basically the diffusion via and the metal one and this thing. What about around this PC? I will add a dielectric. Obviously, there is some dielectric here also, but I will add multiple layers of the dielectric so that the effective dielectric just reduced. So C equals to epsilon A by D. So now that epsilon, so now how you're going to reduce that particular epsilon? So it's like you can use some other dielectric, or maybe you can use the combination of the dielectric. So from the technology point of view, people there are a lot of researches going on, a lot of people are doing these things, how they can reduce these parasitics, how they can reduce these things. So PC is basically the poly. I'm just talking about the poly layers. So there are the different nomenclature people are using. So I'm just using a that particular poly conductor. Basically it is basically the gate I'm talking about. So now this is a device level parasitic. Similarly, if I will talk about uh, okay, so one of the question is, how does these parasitic device level parasitic affect setup and hold timing? So Harish, these are the parasitics. That means it has a capacitance. PMOS has a capacitance. So if I will draw a diagram, if I will just show you. So this is your cap. This is your a inverter. And the schematic point of view, this is basically the inverter. Now, when I was saying there is a gap here, so this is basically when we are talking about the charging of this particular cap, it is basically charging in the sense we are talking about the charging of C load, which is like effective load. Now, what is this effective load? There is a internal capacitance, which is a device capacitance, then the wire capacitance, which is basically the net capacitance. And then for the next inverter, there is a input capacitance. So the combination of this, it's basically the CL, effective CL. So if the device capacitance is high, that means this internal capacitance are high, that means this load is going to increase. If this load is going to increase, that means the CL is going to increase. If the CL is more, then you know the setup and hold and the delay, they have a dependency over the output load. So this is that particular output load. And more, if it is on a higher side, delay is more, obviously it is going to affect the setup and hold time. Okay, so I think I answered your question. The another one is the inductance affect the high frequency in the device level. What about the inductance of effect at the means what exactly you want to ask, Surya? Yes, there are the effects and the high frequency, the inductance effect, and that's the reason we have to calculate the inductance also. So again, now you're talking about the analog side. From that particular angle, you are right, is going to affect a lot. Now this is the cell level parasitic. Now this is what I just showed you. Like, okay, this is basically uh, poly to diffusion. These parasitics are there. Now, if we are talking about metal to metal to metal to the metal one, so those uh, those are considered as a cell level. Now we are not going to talk about the device level parasitics, and that's the reason I just divide the two way, because in the tool we are doing it in that particular way. So once the simulation is done in the dot lib, if you will see the capacitance and everything, that is the device level exception we do first, and we just put it in a some file. But when we are talking about the cell level, so in the cell level, we do that thing on the runtime. Runtime, that means in the after the routing. So the during the after the routing, we are going to do the cell level parasitic extraction. But the cell level, device level extraction that we usually do during the uh, simulation and just put it in a file. But when the tool is going to calculate, the timing or the delay. It will consider the .lib file. In that .lib file, there is an input cap, there is an output cap. That particular input output cap it will consider, and on the basis of that, it is going to calculate. It is going to do the simulation. And this cell level extraction you will see in Sdf file. But yes, device level extraction if you will do, that is also we do in the device level side, that is also present in the Sdf file. So that's device level information, that netlist is there, and that particular netlist is going to give you that information. Okay, so someone is asking how clock transition in CTLs affect this setup and a hold, which are set in the library to say D flip-flop. Clock transition in the CTLs just affect the setup and hold. Venkat, I answered this question, I think a day before yesterday, or I think yesterday itself, when I have mentioned like, okay, the setup time has a dependency over the clock transition, and the transition at a deep in. So maybe you can just go back, just see the video, and you will come to know. Device level parasitics are fixed, and is it varying through different stages? So Harish, no. So it is basically once the placement is done, as such, if I will talk about once the placement of all the cells are done, then if you are not going to change the placement, the device parasitics are almost fixed. It's not going to change. It will change, but not much, I would say. Uh, because of the metal one routing, you can say it can affect little bit, but like sometime that is a very small in nature. Sometime, so it can your question was in a fashion like, okay, in a different stages how it is going to change. So in a different stages as it's not going to change. But yes, it's going to change because of the placement of the cell. So for a particular device, internal capacitance, if you're talking about, that's not going to change. But when these devices are going to interact with the outside world, like the wires and all other things, so because of that interaction, because of that effect, it can change little bit. So, so device level extraction as such, we don't do so frequently because we know if we will make sure all the dielectrics and everything is proper, then nothing is it's not going to affect. But in a lower technology node, it affects a lot. So in a lower technology node, whenever we are not meeting the timing, so like my experience, so I worked almost like a couple of years in the parasitic extraction team. So l- uh, we usually face a lot of problems in the lower technology node where team usually come back and they usually ask this particular portion, like, okay, we did the routing and everything, we changed all these things, even after that we are not able to fix the timing. Then we have to do all these parasitic extraction at the device level, and I have to understand, like, okay, where is the problem? Whether the devices are interacting with each other, and if this problem is because of the device level extraction. So sometime we suggested, not the sometime, because I was in that particular um, uh, I would say that particular team only. So always we suggest, like, okay, you have to make a different layout. You have to place this. This is because of this particular device. So in a lower technology node, it affects a lot. Samir, I don't think it is 115. It is right now. It is 310, 110. So don't worry. So yes. So by 115, I will just finish. I will not take much time. Whatever remaining, I will just do it maybe tomorrow. I know most of the people are here for attendance and the quiz and the certificate. So I will make sure, like, okay, I will just finish it before that. Okay, so this is just one or two slides for the manufacturing defects point of view. So this is basically the ideal one. I just want to show you, like, okay, practically you will get something like this. Okay, so now you can see during the fabrication, there are a lot of issues. There are a lot of defects are there. And these defects foundry has to capture in one way or other way. So like in a technology file, they usually provide you all these informations. So there are different rules, there are the different complex things. So in a tomorrow session, when we are going to talk about the sign off, then I'm going to discuss couple of things like the antenna portions, some CMP related thing. Then there are certain things like DFM related portion. I'm going to discuss, just give you an idea about that particular part. But just want to show you, like, okay, this is something is uh, there are some these type of defects are there. Again, same thing. Maybe you are looking for a shape like this. This is the vertical shape I'm talking about. That means this is a width, this is the thickness. This is the perfect shape, which maybe you are thinking, like, okay, it should be like this. But after the fabrication, maybe you will get these type of shapes. Now here you can see your width and the top, the width is okay, but here you can see your bottom width is not same. It decreases, and obviously if the width is going to decrease, it's going to affect your resistance also, the capacitance with respect to the next wire also. In this particular scenario, okay, here the thickness also different. In this, thickness is okay, but top and the bottom width is not okay. Here you somehow after the fabrication, the thickness has changed, and some width related issues are also there. In this particular case, the top width has changed, it is basically extended one. So there are different rules in terms of and the technology. There are different matrix where we usually talk about uh, width variation, space variation, thickness variation, width and the spacing based resistance variation, capacitance variation. So Foundry usually try to give you as much as data which can help you to do the simulation at a very first stage, so that you can think of, you can design your uh, circuit in such a way, like, okay, after, even after the fabrication there should not be any issue. And all this data they usually provide as a part of a technology file, and through that technology file you're going to calculate the RNC in all these different scenario using the parasitic extraction tool. So the parasitic extraction tool is going to consider all these scenario, and they will make sure they will give you the RNC value correctly in the different scenarios. So let us suppose there are 4 or 5 scenarios, they will give it to you. Now, when you are going to do the timing analysis, then you have to do the timing analysis for all those 5 and 6 scenarios. And that is with respect to the 1 PVT corners, process voltage temperature corners. So let us suppose if you have 100 PVT corners, which we already discussed, like, okay, the process voltage temperature, how those are going to change, how those are going to affect your design, and why we need those corners. Each corner with these interconnect corners. So these scenarios also we can talk about as the interconnect corners. Each PVT corners, then each interconnect corners, then the combination of this become our design corners. And we have to sign off our chip, we have to do the timing analysis, power analysis, area analysis, the functionality, everything we have to do in all those design corners and make sure, like, okay, my chip is working. So till now, whatever you have done on a single corner. You have done in that particular way. Like on an open lane, there is a one library you have done in that particular way. But there are different corners also. So in the industry, if you're going to work, you have to finish that particular, you have to sign off your chip in all those corners. So I think this slide I will just pass it to you just to show you, like, okay, there are certain variations in this particular way. Foundry provide you these variations, and there are other ways also Foundry usually provide, but I think that's not the topic of discussion right now. Fabrication rule, on the basis of these things, Foundry usually come up with certain rules, like, okay, you have to follow, and that is because they want to make sure all of your design should not create any problem. There should not be any short opens and all those things. And these layout rules, which Foundry is going to provide you, now how you are going to check that those layout rules, how your Foundry is going to make sure, like, okay, in your layout, in your design, there should not be any layout related issues. For that, they will give you for each and every layer what should be the minimum spacing, minimum width, what should be the spacing between the two different layers. Like I just took an example of a diffusion, I took an example of a N-well. Similarly, they are going to give you the example of the P, they are going to give you the rules for the P-well, poly, or the metal 1, metal 2, metal 3. So they are going to give you all these things. And on the basis of all these rules, we usually code in a deck. Again, this is a pictorial form, or this is basically some textual thing. Now, on the basis of this, things are going to be like captured in a particular file, like we have discussed for other uh, files also, like a technology file. So these are basically files are known as a DRC file, design rule check file, and we have the tool, physical verification tool. They, after the physically, once you will design everything using these decks, you have to just check it, make sure, like, okay, you are meeting all those requirements. Because if you are not meeting those requirements, In that case, what is going to be happen? Like there can be certain issues which can destroy your whole chip, maybe, or the part of a chip, or maybe it's like a short or the opens, certain part is not working there. So that's a part of a DRC related thing. Okay, so I'm done. Just I took your 2 minutes. It's 15:17 is now. So really sorry for that particular part, but it's okay, I think now. So if you have any question, you can ask me right now. Else, I will request Firoza ma'am just to take the sessions. Yes, I think your quiz is already active. Okay, great.
Okay,
Thanks a lot, everyone.
Yeah, thank you, Puneet sir. Thank you for your wonderful session on this 90th day of the program. So tomorrow there is one change in the schedule. So dear participants, please note that tomorrow in the morning, that is from 9:30 onwards, Puneet sir's session will be conducted. And on the from 10:30 onwards, Dr. Aditya sir's lecture will be conducted. So there is one change. It is also been reflected in the drive. And all the participants are requested to please go through the quiz number 2, which has been already open in the drive. So you will get the quiz link from the drive itself. So you need to go in that link and you need to solve the questions and complete it by 1:45. So the quiz link will be open from 1:15 to 1:45. We request you to please complete it by the time, and please note that no auto submission is there. You need to click on the submit button, then only your response will be recorded. So we request all the participants to leave this platform and go in the Google quiz and solve the quiz. So tomorrow is the last day of this program. So we request all the participants to please be connected by 9:30. The valedictory session will be done after the keynote speaker 5 completes his lecture. So all the participants are requested to please be on time. Thank you. Thank you all. So you can leave this platform and start solving the quiz. Thank you. Thank you, Puneet sir.
Thank you, ma'am.
Thank you, sir. So the event will end in another 2 minutes. Thank you all.